Okay, so let's get started. So what I'm going to do today is finish the 2 or 3 slides that were remaining from last time. And then we'll switch to a new topic, which is going to be communication in distributed systems. But let me start with a few announcements, which we have been posting on Piazza. So if you've been following Piazza, you should already know all of this. So office hours have started this week, the TA office hours. I all had office hours last week as well. So the schedule for office hours has been posted on Piazza. I'll also post it on the class webpage just so that it's in both places. You have the ability to go talk to someone daily. So you can just go take advantage of that as and when you have questions. Of course, you can just post questions to Piazza as well. Okay, that's the first announcement. The second announcement is that we put out a lablet and a lab. Okay, both of them were put up early on the weekend. So make sure you get started on the lablet at least. The lab you can start as soon as you're done with the lablet. Okay, so the material for both of those I'm going to start covering from today. Okay, so today's lecture and the next one will give you most of the background that you need to complete the lablet and the lab. Okay, so if you have any questions about this, do come and ask us. The lablets are always due in 1 week, okay, and labs are due in 2 weeks. Okay, so not a lot of time, but the first lab is reasonably straightforward. But I would not wait till the last minute to start because you might face some time pressure. Okay, so get started early. If you need to make teams, you can do this in a group of 2. You can go and post on Piazza. Several people have taken advantage of that. Okay, so do go and take a look. There is a specific post to search for teammates, so you can do that as well. Okay, you can team up with anyone in any section. There's no restriction. Okay, there are 3 sections of the class. So if you have someone in another section you want to work with, that should be fine with us. Okay, are there any questions about the lab or the lablet? Knowing that we haven't covered the material to do it, but any generic questions? All right, so let's continue. So last time we were talking about distributed system architectures, and towards the end of the class, I started talking about peer-to-peer systems. Okay, so we talked about CORD, we talked about CAN. Both of them are called structured peer-to-peer system because they have a topology associated with it. Okay? But early peer-to-peer systems that predated these 2 systems that are also that also use distributed hash tables were unstructured in nature. Okay, and they basically constructed the topology through a randomized algorithm. Okay, so assume that there are some number of peers in the network. Okay, each peer is connected to a small number of other peers who are their neighbors. Okay, a peer can only talk directly to their neighbors, not to a neighbor's neighbor directly. Okay, you only talk to your neighbor. Okay, so when a new peer will join the network, okay, it can pick k other peers at random, okay, and then call them their neighbor. So then essentially there is a link established from that node to its neighboring node. Okay, and if new peers join, you continue this process. Okay, similarly, if some peer disappears, the link from its neighbors to that peer are all gone because that peer is no longer part of the network. So in this case, those other peers can choose to pick some other random peers and essentially form links with them. Okay? So what this will do is essentially it will allow you to construct a random network, a randomized peer-to-peer network where the topology is determined based by peers themselves by choosing a few other random. And you can choose the number of neighbors that you can connect to. That could be 2, 3, 4, whatever that number is. Each peer is connected to at least those many other peers, who will become their neighbors. So just to give you an example, let's say there are some number of peers. Here, let's just take 4. They're just connected in some random fashion. Let's say another peer joins. I guess here you have to have, because this peer can then decide that it wants to make this one of its neighbor and that another is another. So in this case, it chooses two neighbors, and it's basically formed this network. Now you can ask, how do you actually search for some piece of content? In CORD and CAN, we essentially assume that the entire network acted like a big hash table. You had a key, you looked up the hash table, the value told you the location where that content was stored. And the question really was, how do you get to the peer that actually stores that entry in the hash table? That was essentially what was called query routing in your peer-to-peer net. So here there is no such hash table. Each peer maintains an index of whatever content it has stored. It does not have knowledge about what other peers have stored in the network. So each peer is only responsible for serving content that are stored locally. So now if you want to go and search for some piece of content, let's say food.jpg or food.java, what are you going to do in this network? How will you go and look for such a piece of content? Any thoughts? You will traverse the graph. Yes, you have something else? Okay. So what has been mentioned is essentially you have to first inject a query at one peer saying, look for this data item. And you specify the name. Then you look locally. Maybe you have it, maybe you don't. Even if you have it or not, what you're going to do is you're going to then send that query off to your neighbors. Remember, you're connected to K other neighbors. You send your query to those neighbors. Those neighbors will essentially perform their own lookups, and then essentially add their entry to the results and then propagate it. So your query is going to propagate through the network through a mechanism which is called flooding. Essentially, you're asking all nodes and you flooded the network with your query. So it's almost like you broadcasted the query, except that it is to propagate using that network topology. You cannot ask all your nodes at once. So you send out your query, it reaches some number of nodes in your network, and then you're going to get responses back. You aggregate all of those responses, and then you know where the item is stored. And perhaps the item is stored at more than one node, which is why you don't stop as soon as you find the first item at any one of the nodes. And then what you can do is, rather than actually having all queries propagate through the entire network, you can limit the distance a query traverses by putting a maximum number of hops a query can go. So at each node, you decrement rather the number of hops that are traversed, and when you hit 0, then you don't propagate it in. So that will limit the radius to which the query is going to propagate. Rather than actually flooding it entirely, you can limit that to some degree. So this is how these unstructured peer-to-peer networks are going to work. They're different from our CAN and CORD and so on. Yes, there's a question. Okay. Question is there a way to decide which node to inject the query to? So the assumption is that the users are making these queries. So the user will run some copy of that peer-to-peer application on their machine. So their machine is a node in the network. So you inject the query at your local peer, and then it will propagate from there to the rest of the network. Okay. Yes, any other question? Okay, so you're saying, can it create a cycle, not a deadlock, right? So so clearly the network can have arbitrary topology, right? So if you have a cycle in your graph, your query might propagate and come back to you. But if you keep track of the queries you've already seen, you're not going to propagate it again and just have it circulate. Okay, so you can keep track of outstanding queries, because remember, you're waiting for the responses to come back in the reverse direction. So if you the query is outstanding, so the query just cycles back to you, you can ignore it. Okay, so yes, there can be cycles, but that can be addressed. Any other questions? Okay, so there is a different mechanism that was designed also for unstructured peer-to-peer networks, which was this concept of a super peer. And this was largely done to reduce the amount of query traffic that is flowing through each peer in the network. Because remember, I said queries are being flooded. Okay, so perhaps you store a very small number of items in this entire peer-to-peer network. But because you are part of the network, queries are still going to come to you, even though you have nothing interesting to say to this query. So you might just get these queries and have no real information to add to the query, but there's going to be a lot of traffic that is coming to each of the node in the network. Okay? So to reduce the amount of query traffic each peer sees, okay, there was this concept of a super peer that was designed. And what this is each group of peer simply elects one node among that group as their super peer. Okay? And the job of the super peer is to answer queries on behalf of all other peers in the group. Okay? So what that also means is that that super peer needs to know about not only content that's stored at it locally, but also all the content that's stored within the group. So if you essentially keep an index or a table of all the content that's stored within each group, that super peer can then answer queries on behalf of everyone else. Okay? So in this case, flooding is only going to be done at the super peer level. Individual peers only store content and then answer requests for content retrievals, but they do not answer queries. Okay? Queries are injected into the network, they go to a super peer and they're flooded at the super peer level. Okay? And super peers can do exactly what we said before to answer these queries. Okay? It's still unstructured, except that each group of peers are elected one node as the super peer, as a distinguished node. Okay? So you can say, how do you choose a super peer? You could randomly select one node. You could ask for what nodes have what resources. Perhaps a node that has more computing resources, better bandwidth connectivity can become a super peer because it has those resources to answer lots of queries and so on. There are many different ways to decide how to decide who is a super peer, but that's orthogonal to the general concept of having a smaller number of peers actually handle query traffic, and the other peers are merely keeping the content and answering requests for content. Okay, no question.
You said it's the number of
Okay. Question is, if you have a piece of content somewhere in your network, okay, but the number of hops that a query is traversing is set to some small threshold, and perhaps it doesn't hit one of the nodes that has the content, what is going to happen? Okay. So first of all, queries don't have to give you an answer. Queries might return no result. Okay. That is an acceptable result for a query. Okay. So it is entirely possible that some distant node in the network has a copy of the content you're looking for. Okay. Your query distance is not large enough to reach that node, in which case you will not find that content. Okay, it's very simple. Now, generally, it's assumed that because it's a peer-to-peer network and nodes come and go, typically there shouldn't be only one copy of the content, because if that node disappears, that content becomes unavailable. So there is a degree of replication in the network, which means that by random chance, there should be some node with, if you pick a reasonable threshold, that actually has that node. It's all probabilistic, there are no guarantees. Okay. So there can be replication that can address this issue, but it is entirely possible you don't find the content. So you have to pick the threshold carefully to decide, okay, what size is the network, how much are you willing to flood, and what the degree of replication is, okay, to get reasonable answers to queries. A question? Okay, question is there an advantage to flooding versus just having a list of nodes and then asking them sequentially or in some order. That's the question. So because this is a peer-to-peer network, okay, it is a decentralized network. There is no central entity that keeps track of all the nodes. If that was not the case, you could do exactly what you said, right? Where you have a list of nodes, and then you can query them in certain order and so on. So it's a decentralized network. There is no central authority that keeps track of everything. So you have to do things in a decentralized way, which is why you have to use techniques like this. But if you had a centralized system or a centralized directory, at least of a within the system, you could have different approaches. Yes. Okay. What happens if the super peer is down? We have to pick a new super peer, or the cluster becomes unavailable. So when we get eventually to this topic of what we call leader election, we'll see that essentially the way you're going to pick a super peer is you run an election and elect a leader. That leader becomes a super peer. And all leader election algorithms assume that leaders can fail for any number of reasons. Okay? Maybe the machine fails. In this case, the node just disappears, in which case you run it again and pick another leader. Okay? So the general idea is you don't want the cluster to go away, so you will pick another super peer. Okay, yes, question. Okay. Yeah. The question is, if can you have another layers on top of super peer where they elect another set of peers that have even more distinguished than super peers and so on. You could design any architecture you want. There is nothing that limits it. But having said that, if you keep doing that, you eventually get to a degree of centralization that you're trying to avoid. This is a decentralized system. You only did this to avoid inconvenience at lots of peers. And no other reason. So if you want to keep everything in one place, you can just have a server that's a big directory. Okay? And we'll get to other systems that actually do some of that as well. Okay? Yes. Okay, how does the super peer, if the new super peer gets elected, how do others know about it? There has to be a protocol by which you broadcast your advertise, not broadcast really, advertise your election as a super peer, connect to others, similar to how peers connect to other peers. You can also connect to other super peers. So you have to use similar techniques. Okay, I'm just giving concepts, but you have to take care of all of those things. Okay, all right. So the first system that essentially, shouldn't say first, but one of the early systems that used this notion of super peer was Skype, okay, which was this, I guess some people still probably use it, but it was very popular 10-15 years ago for doing peer-to-peer audio communication. The entire system was designed as a peer-to-peer system. Okay, you can essentially call any other peers to figure out whether your friends were logged in and your contact lists were logged in. You essentially use this peer-to-peer network to discover who is available, who is not available, who you can make calls to, and to then it so happened that suddenly your machine would become a super peer, and then you would see lots of traffic, and then you see that your network is now bottlenecked. So they tried to get rid of that problem by making good node super peers rather than flooding all the nodes with query traffic. The query traffic was are all the people who's logged into the network right now, so you can make a call and so on. Okay. Now eventually Skype went away from that architecture and went to this centralized architecture that was just being requested, where you had some central servers that tracked who is logged into the network, where that node is, what their IP address is, and so on, which allows you to make calls. Right? So it went to a centralized system to avoid all of these problems. Yeah, but it started off as a peer-to-peer network. Okay, one last thing, and then we will switch gears. The last peer-to-peer system I want to talk about is BitTorrent, which is still in wide use today. Okay? It's a very different type of a peer-to-peer system. It's called a collaborative peer-to-peer system. Okay? So there are a few things that are interesting in BitTorrent. Okay? The first interesting thing is there is this notion of what we call altruism. Okay? So essentially, you must contribute to the network in order to get service from the network. Okay? If you are what's called a freeloader, you just like to download content, but you never contribute your resources to the network. Okay, the network will slow you down as a disincentive. Your download speeds are going to reduce. It will take you a very long time to download whatever it is that you are trying to get from the network. Okay? But if you contribute to the network and you try to get something from the network, then the network rewards you by saying that, okay, you can now download from multiple nodes and at full speed and so on and so forth. So it put this notion of incentive, because many peer-to-peer systems saw that users would just get their content and then the node would disappear. They would just stop the peer-to-peer application and no sharing. Okay, so they introduced this notion. Okay, that's one. The second thing that it did was it allowed essentially concurrent downloads. Okay, you could essentially take some large piece of content, and rather than downloading it from one peer, you take that content, you partition it into chunks. Chunks are stored at multiple peers, and you can download them in parallel. Okay? This actually improves the total throughput that you are getting from the system, because you are not limited by some peers' slow bandwidth. Okay? So maybe they have a slow connection to the network. If you pick the wrong peer to download or wrong replica to download your content, it's going to take longer. But if you now try to download these chunks from multiple peers, your speed of the overall throughput that you get from the system is going to increase. Okay? So parallel download, this notion of incentives that were all added to the BitTorrent system. And now the system actually has some combination of some central information and then the downloads and the content itself stored in a decentralized network. So what you have is essentially what's called a torrent file, which keeps track of so for each piece of content, your torrent file. Okay, it's like a table or an index that tells you where to get content from that file. Okay, so that file is now stored at some website. It's a global directory of some sort. That's not stored within the network itself. It can be stored outside the network. So you can say, I want to download the latest Ubuntu distribution. You can get that from BitTorrent. Okay, and then some Ubuntu website will say, here is a torrent for the file that tells you where to download it. Okay? So that torrent file is going to have the address of something called a tracker node. A tracker node's responsibility is to know what peers are currently active in the network, what parts or the chunks of the file are stored at what peers. Okay, so tracker is essentially the node that's keeping track. Okay? Because nodes can come and go, you can't store that information statically. It's going to change over time. So you have an actual machine that's called a tracker that's going to keep track of it. So once you essentially get the torrent file, you go to the tracker tells you here are the nodes, these are the chunks, and you basically connect to those nodes, and then you start downloading the chunks. And then once you have the first K chunks, you can connect to some other nodes, get the next K chunks, and so on until you got the entire file. Okay? So you can download very large files in this fashion. Okay? And as I said, it's always forcing this notion of altruism. If you do not share with the network, the tracker or the nodes will not essentially serve you at their best speed. They might actually throttle the speed at which you can download your content. Okay, yes, question. Okay, question is, do you store larger chunks of the file that have higher bandwidth? Chunks are of fixed size. Okay, but having said that, the BitTorrent application can figure out the speed at which is downloaded. Let's say each chunk is 1 megabyte. Okay, you start downloading the first 4 chunks. Maybe the peer 3 has a very fast connection, so that chunk will download much faster than the other. Then you can essentially go back to the peer and get the next chunk that you want in the file. Okay, so you don't have to store larger chunks, but you can download more from nodes that are giving you better service. Okay, so that's up to the client to do. Can decide all of that. Any other questions?
So in BitTorrent, like there is a saying that if we are downloading particular thing, we can play it together with it, like download. So does that particular chunk download first, then plays it, or like it can also go in parts? Like
the question is, in BitTorrent, you can download and play at the same time, and how does the downloading and playing happen at the same time? So BitTorrent can be combined with other applications like media players and so on, which are downloading and playing. not streaming, but it's downloading and playing. But typically you would have wanted enough of that chunk to be downloaded before you can start playing. Because if the chunk downloading slows down, then your playback will essentially stall. Okay? So you want to deal with that. When we get to video streaming, we'll think about these issues more. And not through BitTorrent, but how to do good streaming. Yes, question. Okay. The question is, what does the torrent do and what does the tracker do? Torrent essentially stores information about the trackers, okay, and tells you what is the file, which are the trackers. And the trackers are the ones that are keeping track of which nodes have it. You cannot statically put this information. Torrent is actual file. Okay? So you can't keep statically an information about all the nodes that have chunks, because that information will change over time. You cannot be guaranteed that those peers will be part of the network when you want to download it. So you want to have a file that points to the tracker. The tracker is an actual machine that's checking which peers are up and which ones are sharing. So it will tell you where to get the chunks. Question is, yes, the tracker has to be part of the network. So trackers are assumed to be more static entity. They don't have to store content, but at least they have to track the content, track the peers that store the content. Yes. Okay, is there a variant of the system where you can have a distributed hash table that stores all the files? Just 1 second. You can have any variant you want. Not sure why this is going. Try that. Yeah, it doesn't work. Every time I turn, it disappears. Okay. Let's hope it stays that way. Okay. So yeah, you could have other variants where DHTs can store information. Maybe the tracker has a DHT in it. Okay. How you implement the tracker is not part of the BitTorrent protocol. Okay. All right. Anything else? Yes. Who owns the tracker server? So that's part of the network. So they are all peers that are contributing. You could also set up trackers separately from the peers. Right. So it's a decentralized network. There's no central authority that has trackers or anything like that.
How they currently control the tracker server is
yeah. So there's no security in BitTorrent, right? You can essentially have nodes can give you garbage and say it's a chunk, right? So there is no. So you have to have additional techniques where you are verifying the chunk is valid. All that has to be done outside. Just a way to share. You can layer additional security and other tech verification on top of that. Okay? It's not part of the protocol itself. Okay? Yes, question. Okay, question is who is storing information or where you sent it and so on. Typically that's tracked by IP address and clients. If your IP address keeps changing, then I don't exactly know how it tracks it. But now let's assume it doesn't change. But then when you join the network, you can have some information about what this application has done in the past. Okay, so that's a very simple way. There may be other ways. I don't exactly know how they can track it if your IP keeps changing, if you're on a NAT device and things like that. Okay. Yes. So can you repeat your question?
like
How do they earn money? So this has nothing to do with money. Right? This is just sharing content. You don't get money for sharing it. It's an incentive is just that you get good performance if you share your resources. There's no monetary incentive. It's an actual incentive for sharing resources. Okay. All right. So last slide here is on autonomic distributed system. It's a different architecture from whatever we were talking about. This is not a peer-to-peer system. This is just a way to make a distributed system more self-managing and adaptive in nature. Okay. So these are called self-star system, and star just is a list of properties. It's just an expression for saying the system is self-managing, self-healing, and so on. Okay. So what happens in this case is that the system itself is capable of monitoring itself. Okay. And it can figure out what is actually going on in the system and take autonomous action without any human intervention. Okay. So you added intelligence to the system. Okay. System can track what is going on and correct problems. So for example, you can have a self-healing system. Let's say it's a web service. It's a self-healing system where it's monitoring whether all the nodes are up or down. If some node in your web service goes down, it can essentially heal by just restarting that service on another node or rebooting the node and so on, without waiting for a human to come and figure out what's going on and fix it. Okay? So this is essentially a notion of what is called autonomic distributed system, where the system has more autonomy, is autonomous in some shape or form. Okay? We'll look at how to do some of this later on in the course. Okay? I just want to introduce this concept here. All right. So that's the end of lecture 2. So let me now switch to lecture 3. Which is the topic we really wanted to go into today. It's a new topic. It's communication in distributed systems. So we will talk about message-oriented communication. We'll talk about remote procedure call. And depending on how much time we have left, we'll get into some implementation details of RPCs. Okay. Next time, we are going to talk about things like RMI, which is what RPCs are called in an object-oriented world. And we'll talk about stream communication and other topics. Okay. All right. So let's start with how you can essentially build the communication aspect of a distributed system. Remember, when I gave this definition some time back, I said it's a collection of machines that communicate with each other. Okay. How is that communication enabled at an application level or at a system level? If you want to write a distributed application, you have to have some way by which components of your application interact with one another. Okay. How is that done? Okay. There are two ways we are going to talk about. Okay. Unstructured communication, which is just going to use shared memory or data structure. Okay. You put some data that you want to share with some other entity into a piece of memory, and some other entity gets access to it over a network. Okay. That's one way to share information. Okay. That's unstructured. The structured way is essentially passing messages. Okay. You want to communicate with some other entity, you take whatever you want to share, put it in a message, send it to the other end, and that other end is going to receive the message and process it. Okay. So we are mostly going to focus on structured communication, not on unstructured, because unstructured communication is easier to do on the same machine, where it's easy to share memory across different processes. But across machines, it's harder because you have to give someone else access to a memory buffer on a machine, for example. Okay. There are other ways to do it, but that is by and large how it's done. Okay. So let's mostly focus on structured communication. I'm going to talk about low-level ways to do this and higher-level ways to do this, which are RPCs. Okay. So before I do that, I'm going to spend 2 slides talking about communication protocols. Okay. If you've taken a course in networking, this should be completely familiar to you. If not, I'm going to give you the 5-minute version of how communication or network protocol works. So what this figure shows is what is essentially called a network protocol stack. As you see, it's basically using a layered architecture for communication. Okay. TCP/IP is an example of a network protocol stack. It's the most common one. Okay. There are others, but that's the most common one. That's what we assume for this class. Okay. So as you will see, these 2 ends are essentially 2 machines on the network. Okay. their operating systems are going to essentially implement a network protocol stack. Let's call it TCP/IP stack for just for them. Okay? And see, this stack is going to have multiple components. At the very bottom is what is called the physical layer. Okay? That's the layer that's used for actual communication. That could be your Ethernet cable. That's your physical medium for communication. Or it could be a wireless channel if you just have Wi-Fi, or it could be a cellular channel. That's the physical layer that is used for communication. Okay? Now, sitting above the physical layer is essentially what's called the link layer. Okay? So this is the protocol that's going to be used to communicate over the wire or communicate over the air. Okay? It's essentially what's going to send bits on either your wires or on a wireless channel. Okay? So that's your data link layer. So Ethernet protocol. Okay, Ethernet wires are the physical layers. Ethernet protocol is essentially what allows you to send bits over that wire. That's your link layer, okay, also called MAC layer. So disappeared. Okay. Okay. So the layer above that is called the network layer. Okay. So the network layer is used for routing. Okay. So if you're sending message from one end to the other, okay, those two ends are not going to be directly connected. They're going to be connected to a sequence of routers. Okay, your message has to go from one hop to the next, and that essentially is done at the network level, which essentially implements what is called routing. So each router along the way is going to decide what's the next hop to send this message. So you do hop by hop routing, and your message is going to start from a sender and eventually get to a destination, okay, using one hop at a time routing. Okay, that's your network layer protocol. Okay, what is on top of network layer is transport layer protocol. And transport layer protocol is responsible for end-to-end communication. Okay, network layer is hop by hop. So you have essentially a network sequence of links. Each of those links runs a network layer protocol that forwards. So it's doing forwarding. Okay, this is doing end-to-end transport, where you can look at, I sent this packet, did it arrive at the other end? If not, you want to retransmit. Okay. So you want to essentially check for packet losses, do retransmission. You can essentially do what's called rate control, which determines what speed should I send my packets at. That depends on how much bandwidth you have in the network. Okay, you have to figure that out and adjust as the network conditions change and so on. Okay. So IP is an example of a network layer protocol, and TCP is an example of a transport layer protocol. Okay. So in the TCP/IP stack, that's why TCP and IP sit. Okay. So above this is what is called a session layer, where if you have an application that set up a session for communication, you can do additional things with it like compression, encryption, and things of that sort. So that's at the session layer. You have then a presentation layer which decides how this data is presented to the application. At the very top is the application layer protocol. Okay. Now the way this protocol stack works is, if essentially it's the two applications that are trying to communicate. There's an application here, let's call it a browser. There's an application at the other end, let's call it a web server. They are the ones that are communicating. Okay? So the browser is going to make a request to the server. That's essentially going to be a message that it wants to send to the web server. Okay? That is an HTTP message, because web servers and web browsers speak HTTP. Okay? That's the application level protocol that's used. Okay? The HTTP message is then going to be handed to the layers below it. They get processed all the way to the physical link layer, get sent over the network, and then appear at the other end. There will be multiple nodes along the way that are all routing. They appear at the other end, and they're processed on the way up, and then they're handed back to the application. Okay? So each layer is going to perform some processing on this message and then send it to the next layer. Okay? Typically in the TCP/IP protocol stack, you don't have the presentation and the session layer. The application directly talk to the transport protocol. Applications are directly talking to TCP. Okay? Any encryptions, all of that has to be done by the application, because the session and the presentation layer are missing. Okay? Is that clear? Okay. So here is an example of what our message might look like as it goes over the network. Okay? So first is this box called the message. That's the actual message the application as one end is sending to the other. Okay? That could be your HTTP request or a response. Okay? So then you add a header. So each message is going to have a header. So you add a HTTP header. Okay? That's what HTTP does. It hands it to TCP in this case So these two layers are missing. Okay, then you get to the transport layer. The transport layer will then add its own header to it. Okay, then you hand it to IP. IP is going to add an IP header. Okay, the IP header is essentially the network layer header. Okay, that's going to tell you what's the source IP, what's the destination IP where it needs to go to, and so on. Okay, then you hand that to the network layer, which is in this case, let's say Wi-Fi. Okay, and you're essentially going to add a header to it, and then you will send it off. Okay, that's basically going to then go off on the physical channel, and then as each layer receives it, is going to look at the header, decide based on that header what to do with that message. Okay, strip that header and give it to the layer above it. Okay, so as the message is now going to go up the protocol stack, each layer will process it, remove the header, give it to the next layer, and so on until it arrives at the application. Okay, so that's essentially how packets are going to flow through the network, and that's really all you need to know as far as this class is concerned. Any questions? Yes.
The layer can be changed or different like that. Transport layer can come after the layer.
Okay. The question is, can the ordering of layers change? The ordering of layers will not change. That is the protocol stack. It is designed to essentially process things at the physical medium, the network level, end to end, and so on. Okay, so you don't actually change the ordering of the layers. I don't understand the question. You're saying something about hardware encryption. If the what, I don't know what you mean by. Yeah, so typically if you want to do encryption and want to send it over the network, you're going to encrypt the message. You're not encrypting other aspects of it. Okay, so you have to encrypt the message and then send it off. The protocol stacks themselves don't use encryption. If you encrypt it after the data link layer, nobody can see what is in there. Okay? Now you can use hardware to encrypt the message itself, but it's not going to happen at some other level of the protocol. So the application has to use hardware to do encryption. That is fine. Okay, so let's skip the middleware protocol. Let's talk now about how TCP can actually use this concept to communicate between two endpoints. Okay? Or put another way, how can you write a very simple application that's using TCP/IP to talk to between an client and a server, or between two components of an application? Okay? So the way this is done is to an abstraction called a socket. Okay? And think of a socket as analogous to how you a file. Okay? In the Unix world, the way you're going to interact with socket is very similar to the way you will interact with the file. Okay? Files are what you use to store data on disk. Okay? Sockets are what you use to communicate data on a network. Okay? That's the difference. Okay? And both are used in a similar way. You first create a socket just as you create a file. Okay? And then you read or write to a file. Similarly, you read and write to a socket to send or receive data from a network. Okay? So that's the basic concept you want to keep in mind. I'll show some examples of how this is. Okay? So the socket is the abstraction where we have is the abstraction that we are going to use to essentially communicate between two machines. Okay? And here is how it is going to work. So there are many steps to construct a socket and send and receive messages. That is best illustrated with the picture. That's going to show you how this works. Okay? So essentially what this is, the top is the server and the bottom is your client. Okay? So both the server and the client have to create a socket, and you do this by calling the socket method. Okay? That essentially creates the two endpoints that we are going to use to communicate. It's like creating a file. Okay? The server is going to then call bind, which will bind that socket to a number. Okay? Just as every file has to have a file name, every socket has to have a unique number that identifies. Okay? That's called an endpoint, or also called a port number. Okay? So every socket has to have a number, and that's basically how you identify the socket. So that is what you use by bind for. Okay? Once you're given it a number, then you can start listening to on the socket, which means you're waiting for messages to arrive. Okay? That's what listening on a network connection means. Okay? And the client essentially has to create a socket, and then it has to connect to the server, saying, I need to communicate with this machine, and then you use the connect call to do it. Okay, once you use connect and accept at the server, and you have essentially established a TCP/IP connection between the client and the server, and two socket endpoints for the TCP/IP connection that you are going to use to send and receive messages. Okay? So once this is done, you can simply use read or write. Okay? You can read from a socket to get messages. You can write to a socket. Just as you read and write to a file, you can read or write to a socket. And then in this case, you're essentially getting data from a network connection, not from a disk file. Okay? But it's the same concept. Okay? So you use read and write, multiple reads and write to send and receive messages. Once you're done, you close the socket. Okay? Yes, question. What is the difference between a socket and a port? Okay, a port number is the identifier of a socket. Okay? A socket is the abstraction you're using. Every socket has a unique number, which we call its port number. That's its name. Just as a file has a name, the port number is the name of that particular socket. Okay? And these numbers can be anything, except that there are certain port numbers or socket numbers that are reserved for use. So you cannot use them for arbitrary purpose. Okay, port 80, okay, or if you give a socket number 80, that means it's essentially a web service. It only speaks HTTP. Okay? If you use port 22, that's what you use for SSH, okay, to establish an SSH connection. So certain network services have well-defined ports. Okay, so you know that if you connect to that port, that's the service on that machine you're connecting. Okay? But other application, you can use whatever port number you want. Okay? So above, let's say, certain reserved range, you can essentially use the rest of the numbers to create sockets and so on. It's like saying certain file names are reserved. You can't use that file name for your file, but you can then use any other string. It's the same concept. Okay? Yes, question. Question is, how many users can connect to port 22? You can have any number of users who connect, because what happens is, it's not shown here, in a service, as opposed to two static endpoints. In a service, once you receive the connection, you will actually create another socket that's specific for that connection. So you can receive on other. Okay. Anything else? All right. So here is a simple example of what I showed in the previous slide with the picture. Okay, it's not, I mean, this is Python code. It's the same code, I think, that's in your lablet, which you will use to figure out how this works. So you will see the client code, you use socket to create the socket, and they use connect to your machine and a port number. The port number there is 80. They're connecting the web service on that domain. Okay? And on the server, you're going to have a server socket. Okay, you bind that socket to port 80, saying this is a web server, so it's going to essentially get number, essentially socket port number 80, and then you listen. And then you sit in a loop waiting for clients to connect, and then you essentially can have multiple clients connect on port 80, and then you can service them. A very simple client-server application using sockets. Okay, what this is not showing is, after this point, you still have to do reads and write to actually send a message. It's only showing you how to establish the connection. Okay, there's no communication yet. Yes. What do the numbers mean inside the bracket? 80 is the port number. That's the ID. That's what I was saying. Every socket needs a unique identifier, numeric identifier. Okay, that's the port number. Yes, why is it saying 5? I think that's a timeout, if I'm not mistaken, but I will check. Okay. Yes. Yes. Question is, how are the requests processed? And here you are going to sit in a while loop, and each connection you are going to process sequentially. Okay. In your lab, you will actually write a threaded application that can do concurrent processing. Okay. This is not going to be concurrent, but that's what your lab is going to ask you to do for exactly the reason you are asking. Because if you do this sequentially, every other request that's come has to wait until the previous one finishes, because it's doing sequential process. That's not what you want from a server. Server has to process requests concurrently. For that, you have to add threading to this model, which is not shown here. Okay, yes.
Does that kind of
Yeah, the question is every time you basically create this client connects to it, is there a socket connection? So yes, so every client, so there could be many such clients that are connecting to a server. Each of them has their own TCP/IP connection to that server.
what is the same kind of that's simple that
Okay, question is what if the same client has multiple requests? That depends on how you write the client. If the client is sitting in a while loop and just sending one request at a time, it's a sequential client. The client has multiple threads. They can open multiple TCP connections to the server and send requests on each of those. That is how you write the application. Right? The socket abstraction doesn't limit you from sending concurrent requests, sequential requests. It's just a way to establish a connection. How you communicate is up to how you write the application. Right? So you will actually look at all of these in the next few lectures and in the lab. Yes, question. Question is how many processes can listen on the same port number? That's your question. Okay. So as I said, each socket has to have a unique identifier, which means that there can be only one process that is associated with a socket of a certain number at any time. So there can be only one web server that listens on port 80. If you want to start another web server, you have to give it a different port number once that port is in use. You can have any number of web servers running, just that they can't all listen on port 80. You have to assign some other port. Okay, so one process and one that has a socket, that is basically going to be one port number. Any other questions? Yes. And the client have more than one connection to the same server, you can have as many TCP/IP connections as you want. You will just repeat that code. You can create two small socket twice and connect to the same server twice. That's certainly fine. Okay. Is there any limit to it? There is no, for most reasonable applications, there is no limit. The OS is going to put a very high limit, which basically is equal to its memory size or something. So if it runs out of memory, you cannot create. So you can't put an infinite loop and keep creating connection. Eventually you run out of resources, but there is no real limit in that sense. It's only limited by what your machine is capable of. Yeah. Okay, so that's sockets. Yeah, I'm going to very quickly go through what is happening underneath at a TCP level to establish this connection. So what happens when you essentially do connect here, okay, and then you do an accept here. Okay. So essentially what is going to happen is TCP/IP has to then establish a connection between the client and the server, an active TCP connection over that socket. And this is done through what's called a three-way handshake. Okay. The three messages that have to go back and forth between the client and the server to establish a connection. The connection is a duplex connection, which means it's bidirectional. Okay. You can send and receive data on that same connection. Okay. So the way it's going to work is you send what is called a SYN packet. The client is going to send a SYN packet to the server, and SYN just says, let's open a connection. So SYN stands for synchronize. Okay? Since it's a duplex connection, the server, once it receives that, is going to send a SYN packet in the opposite direction, okay, saying, let's open a connection. So that's why it's duplex. Okay? Now, in TCP, every packet must be acknowledged, saying it was received. That's how TCP knows that the packets have been received, otherwise it will retransmit. So every time you receive a packet, okay, you have to acknowledge this packet as well as any previous unacknowledged packets. Okay? So you will see that there is a SYN and there's an ACK for that SYN that came. So you acknowledge the SYN packet in addition to sending your own. Okay? And then the client essentially has to send a acknowledgement to the SYN. Okay? So there are three messages. You send a SYN one way, the SYN another way, send an ACK. So that's a three-way handshake. Once that is done, you're going to have an active connection between the client and the server. Okay? So you see now the next one is an actual request message. So that's a real message that the client is sent over the socket. Okay? Perhaps it just wants to send one request and is done. So essentially, it starts tearing down the connection in this case, even before the response is received, by sending a fin saying, here's a request, I'm done sending. Okay, so from the client to the server, the server is going to acknowledge the request and the fin saying these were received. It's going to send an answer at some later time. It has to then tear down the connection by sending a fin and get an acknowledgement. Okay, so to send one request from the client to the server and get one response, okay, you essentially sent 9 messages. Because there's a 3-way handshake at the beginning, there's a 3-way teardown at the end, and then all sorts of acknowledgements that are to be sent. Okay, so that's a high overhead. So the only useful work you did in this entire process was to send one request and get one answer. Okay, but creating that connection and tearing it down has imposed additional overhead. We will come back to this when we talk about things like HTTP. So if you make a repeated HTTP connection, get a small piece of content, make another one, you are actually having to pay all that overhead. Okay.
So
Yes.
if there are multiple requests, so it would go after one request after one, or like it would be like complete process, then the second request, then the whole process.
Okay. Question is, what is going to happen if there are multiple requests? Typically, that answer depends on the protocol. But if you're doing sequential processing, you'll wait for send a request, wait for an answer, then you can keep the connection open. You don't have to start a new connection. You can send another request, get another answer, and so on. So you can have multiple request response round trips on the same connection before you tear it. Okay? You are asking, can I send the second request even before the answer has been received? Only in some protocols. Okay, because then you have to track if an answer comes back, which question, which request was it for? Yeah, you have to have additional things in there to make sure you know what answer is for. Yes, question.
What if the only package that requesting?
Okay, question is, what if you don't get the answer, or what if something doesn't work the way you want? So all of these responses will have messages are going to have timeout. So if you don't get an acknowledgement by a certain time, you're going to time out and send it again. Okay. So if you don't get an answer, okay, in this case, the server has actually acknowledged your request. So you know that the request was received. If you don't get an answer, you're not going to send the request again. You might just assume something is wrong and you will time out at an application level and resend the request. TCP is not going to send the request. On the other hand, if you did not get an ACK for this request, you assume that the request never reached the server in the first place. So you will retransmit that request after a timeout value and you keep doing this until you get an ACK. That's how TCP works. It's going to timeout and retransmit packets until you get an ACK, you know the message was received. Okay? So if the message was received but you didn't get an answer, TCP is not going to solve that problem. It's up to the application. Okay? It's like you send a HTTP request. Okay? TCP is delivered it. Your page is not loading. Okay? That's basically no answer has come back. Either you will say, I will abort and then click on the link again, or you will do something like that. Right? So you are now putting that on the application or the user's burden, not the TCP is not going to do anything. Okay? Question. Does the server not wait for an acknowledgement that it has not gotten an answer? So you will have to acknowledge. So as I said, an acknowledgement, so there are packets are sent in sequence. When you send an acknowledgement to some message, it means that you received all the messages before it. Okay? So if you send an acknowledgement of the fin, that means you are acknowledging both the fin and the message because they were sent in sequence number. There are sequence numbers that are added to. That's where the headers are used for. Okay? So you don't have to send 2 acknowledgements. You can send 1 and be done. Yes.
On which one you're doing?
The question is, at which line do you assume that the client and server have created a connection, right? So that is going to be essentially the connect and the accept are the places where you say I established a TCP/IP connection, right? So that is where the 3-way handshake has happened. Okay? Everything after that's not shown here. Then you have to send a message, do read, writes, and all of that. Okay. Yes.
What is
Okay. Okay, so question is what is AF, INET, and SOC stream and so on. So the one thing I didn't mention is there are different transport protocols that are part of the TCP/IP stack. TCP is only one of them. There's another one called UDP, which is slightly different from TCP. The socket abstraction is common across the entire set of protocols that are supported. So some of these are going to say which type of socket do you want to create. So this is basically all of that is fancy terminology for it's a TCP socket, not a UDP socket. Okay. Yes, question. Why do we what? Why do you need message number 3 from the client? So every packet that you receive has to be acknowledged in TCP. That's the rule of TCP. Okay, question, why does the server need to send a SYN message? SYN just says, I want to establish a one-way connection to you. Okay, the client has established a one-way connection to the server to the first SYN. Okay, that only will let the client send messages to the server. The server wants to send messages back. It has to create a one-way connection. That way, it becomes a duplex connection. Okay, so that is why you're going to have to send one SYN from the client to the server, another one the other way around. Will the protocol still work if the ACK is lost? Okay, so essentially, if any message is lost, you are going to time out and retransmit. You don't proceed. Okay, so there are timeouts built in, and you are going to retransmit that message because TCP will know that some message got lost. Okay, so you are not going to proceed until that message is eventually received. Okay, yes.
Does that mean if we are like the client is package and the first one gets lost, but like you get the response for the other two, that means like process will stop there until they wait for the first.
So typically, the question is if you have some sequence of messages and some message in the middle is lost, let's say. Right? So the first few messages that were received will get acknowledged. Okay, you might have sent the next 4 messages, but you are then waiting for the acknowledgement for the message after the previous acknowledgement. If you don't get an acknowledgement, say for message number 5, messages 1 through 4 have been ACK, 5 to 7 have been sent. So you are waiting for an acknowledgement for those messages. So if you get an ACK for 7, that means that everything before it was received. Okay? But if you don't get any ACK at all you assume is the next message that is unacknowledged is the one that's lost. So you will send that. Okay? So you will send 5 again, and then hopefully you'll get a acknowledgement for 5, and then since the others were received, you'll get another ACK. Does it slow down the process? So this is what reliable transmission does. You have to send ordered messages. Right? That's how TCP works. Okay? This is not a course on networking, but if you want to understand this better, you should actually get into more of a networking discussion within a networking class. But there are only so many ways you can do reliable communication. You want to ensure that anything that is lost, corrupted, is resent. That's the way you're going. That's what TCP does for you. Okay? You don't need to know much about TCP at all because you're going to program at a socket level. You don't actually care. But this is what you need. At a minimal, you need to know is happening under the hoods. Okay? Any other questions here? Yes. When will the server refuse to connect to a client? Is that the question? So long as the socket connection on which it is listening is open, it can continue to receive new connections. Okay? So if you just close that connection, you close that socket on port 80, then you stop listening. Then if new client tries to connect, they get an error. Okay, so the only way the server can stop is to actually close the connection. Okay, correct. So there's something called group communication, which we will get to in a future slide. I just want to mention what it is. Okay? So whatever we talked about so far is one-to-one communication. It's called unicast communication. Okay, one client talking to one server, one application at the other end. Okay? Sockets allow you to do one-to-one communication. Okay? There's also a way to do one-to-many communication where you send a message once and there are multiple recipients. It goes to multiple recipients, not to one endpoint, multiple endpoints. Okay? This is very similar to sending email, where you can send an email to one recipient, or you can send it to a mailing list. You send it once and it goes to n recipients on that mail. Okay? So if you do the latter, you are doing what is called multicast. Okay? Not broadcast, is multicast. Multicast says that there are n receivers for every send of a message. Okay? That's called group communication. You communicate with an entire group. Okay? And we'll get to how to do this at a later time. Okay? There are many interesting questions on how to do this, but not for today. Okay? We'll get to group communication maybe in a future lecture. Okay? So what I'll do for the rest of this class is talk about the next concept, which is remote procedure calls. Okay? Socket communication is like doing assembly programming. It's the lowest level of communication. Okay? Typically, you can program at a much higher level than socket, but sockets are still very popular for a variety of distributed applications. Okay? Having said that, what other abstractions are available to you as a programmer to write client-server application? Okay? One such abstraction is called remote procedure call. Okay? The goal here is to make writing distributed applications as simple as writing a single centralized or single process application. Okay? Now you all know how to write a program. Okay? You have program, it has functions, one function calls another function, you pass parameters and so on, and you make the program modular by essentially having these functions or methods that take the entire functionality and have smaller pieces of code. That's how you essentially write a normal program. Okay? What if writing a distributed application was very similar? Okay? Now, the thing that is different when you write a distributed application is you essentially have to deal with network communication. Okay? You have to essentially have some parts of your application run on one machine, and they have to communicate with another part of your application that runs on another machine. Okay? So far, you know one way to do this, which is you're going to use sockets to send messages back and forth. Okay? One program here is going to create connections and messages. That message gets processed, reply comes back, and so on. You know that. Okay? How can we make that simpler? Okay? The way we are going to do this is essentially create a new concept called a remote procedure. Okay? As the name remote procedure suggests, this allows a program to call a function that actually resides in some other process on some other machine. Okay? Normally, when you call a procedure, function, method, you're essentially calling something that's within your address space, within the same process. Right? What if you could actually call a function that resides on another? This gives you another way to communicate, because now you're directly invoking a function that's in some other process. Okay? That is essentially what a remote procedure allows us to do. Okay? And here's an example of how it's going to work. Okay? Here's a server machine. Okay? Let's say it implements a service called add. Okay? Add is going to take 2 arguments and return the sum of the 2 arguments. Okay? Now, a client wants to essentially send 2 numbers that it wants the server to add to and send back a response. Okay? Normally, what would you have done? Okay? You would have essentially had the client make a connection to the server. The server has to be listening to that socket connection, and you establish the connection. Then you construct a message, okay, which is essentially a buffer. You say, I want to essentially add, and then you say, this is what I want to do, send the message. The message gets processed, and then you essentially get back a reply. Okay? So you as a programmer have to write all of that code that I showed you 2 slides ago. Okay? Now, in this case, you are not going to do any of that. You are simply going to call add ij. That's it. It's like you call the local function add, and you pass 2 arguments. Okay? Something underneath is going to figure out that this procedure is not part of this client process, not a local procedure. It's a remote procedure. It's in some other process's memory. Okay? It will then construct that message for you. Okay? It will create that socket connection underneath for you, which you don't see. Okay? You don't actually worry about it. All of that will happen under the hood, and you'll see that this message that has been constructed saying, here's an add procedure that needs to be invoked. Here are 2 arguments. That message goes. it comes here, and the server process, whoever wrote that, doesn't have to deal with all that. You just assume that you have to write the add function and something is going to invoke it. You execute, return a value, and it goes. Okay? So as a programmer, all you're doing is you're writing methods and calling methods, okay? Which is exactly what you do when you write normal programs. Okay? The runtime system, okay, and a special compiler will write all of that extra code to ensure that when there are remote methods are being invoked, then some message has to be created and that has to be sent off to the server, and the replies have to be gotten back. All of that is done for you. Okay? So you are now programming at a higher level of abstraction. You just have to say, what methods do I want to expose in my server? Okay? Here are these methods. You just write the code for the method, and then you are going to tell some runtime compiler or some other tool saying these are the methods that are being exposed. Okay, not every method has to be exposed, right? You decide which method you want to expose over a network, and then you basically just start the server. Okay, and then the server will, all the code for listing to request, all of that is written for you automatically. And at the client side, you don't have to worry about connecting to servers. You just call the method you want, knowing that in this case a remote method, but all of the code is again generated for you to invoke that method on another machine. Okay? So this is called remote procedures. Okay? So now each of the client and the server has some local procedure, the local function like any other function, and some procedures on the server are going to be remote, and some invocations of function on the client end are going to be invocations of remote methods. Okay? Is that clear? Okay. So what there are a few concepts that you want to see here. Okay, one is that there is a part of the client process and the server process that is called stub. Okay? That stub code is the auto-generated part of your application. Okay? This is code that you would normally write if you're doing all of this at a socket communication. Okay? But when you are using RPCs for communication, the lower part below this line is essentially all auto-generated. That's called stub code. Okay? And so you will see that there's a client has a stub and the server has a stub. The server stub receives messages, it processes them, and then invokes the right methods, gets back the response, constructs a reply, and sends it back. Okay? The client stub has to first figure out where is the server, okay, because client has not been, you are not writing anything about what IP address, none of that is written necessarily by the user. Okay? A lot of that is auto-generated. So you can figure out that you have to look for the add service, track it down, open a connection. All of that code is written for you in the stub code. Okay? So the steps here are client is going to call procedure. Okay? The procedure happens to be a remote procedure. It goes to the client stub. The client stub builds a message. Is that message and sends it over a network, okay, which means that it has to actually establish a TCP/IP socket connection. That part is not shown here. You send the message. Okay, then it comes to the server stub unpacks the message, okay, and it invokes a call to the actual procedure. Okay, the server will then execute the procedure, a reply comes back, goes back to the client. Okay. So all of these are steps that an RPC method is going to invoke. Right? Okay. So here is the timeline of how this is working. Okay. So the x-axis is time. Okay, the top is the client, bottom is server. So this is standard blocking communication. It looks exactly like you invoke a method that's local. Okay, server is the client is executing here. That's the dark black line. It invokes an RPC call. Okay, and then it blocks, waiting for the reply. This is the same thing that's going to happen if you invoke a local function. Okay, you wait for the called function to return. Okay, you're not going to execute in normal. Unless you're doing some asynchronous programming or something like that. If you're doing standard programming, you call a function, wait for it to return back. Okay? You called a function and you're waiting for the result. The result in this case is coming from over a network, not from a local function. Okay? Message goes to the server is executing, sends back a reply, and then it waits for the next request and so on. And the client will continue. Okay? These are standard blocking RPC semantics. Okay? The client is going to block, waiting for the server. The server is only going to execute when it requests, when a request comes to execute an RPC. Okay, question. The question is, does the connection stay open from the client side? That is dependent on the stub code. right? So the stub code can decide for every RPC, set up a new TCP/IP connection, or there are multiple connections. You can choose to keep it open and send the next RPC request on that connection. Okay? As a programmer, you don't actually worry about this. You just make your calls and let the stub decide all that for you. Yes. Okay, that's a good question, and I'm going to get to that in a minute. The question is, when you write a message from the client, do we need to know the format? And the first thing is you're not writing a message, you are invoking a function. Okay, the function definition is known to you, that this is a function that has name, it has n parameters, first parameter is integer, second is string. So that is known to you as a client. So you just construct a function call and you just call it with the right parameter. That you can do, right? And then rest is taken care of by the stub. Yes. Question is, can the client write another function that overrides it? If you have two functions with the same names, that will not compile, right? So it's the same thing. If you have a remote procedure that you declared and then you write another add, compiler is going to complain. Okay. So few things to keep in mind. Okay? More or less, remote procedures look like local procedures, but there are some differences. They're not exactly the same. Okay? Here's an example of a conventional procedure call. So you should know that when you invoke a function, okay, any parameters that you pass to a function are pushed to a stack, and then the called function takes those parameters from the stack, processes it, puts the return value on the stack, and so on. So you stack, okay, within a process as the way you are going to send arguments back and forth. So a remote procedure, there is no stack. Essentially, all of the information is going over a network. Okay? Keep that in mind. Okay? And why is this important? Yeah, because there are two ways you can essentially do parameter passing. You can call by value or you can call by reference. Okay? When you call by value, you make a copy of that argument and you send it to the called function. When you pass by reference, you essentially pass a reference or pointer to the called argument. Okay? In normal programs, depending on the semantics of the code you're writing and whatever the language supports, you might have both of those supported. Okay? You can pass pointers or you can pass arguments directly. Okay? Now, in remote procedures, only call by value is supported. Okay? The reason is, if you call by reference and you pass a pointer, okay, at the other end, if you dereference that pointer, that's meaningless because that pointer points to a memory address on the client machine. Okay? If you dereference that pointer, that address on the server machine is not actually the same address that the client intended to pass. Okay? And there's no concept yet of essentially dereferencing pointers over a network. When you dereference a pointer, you're essentially looking for that address in your memory address space. Okay? So RPCs are going to prohibit you from sending arguments that call by reference. All RPCs are call by value only by default. Okay? There are some exceptions, but this is a good rule to keep in mind. You can only call by value, not call by reference, because you cannot pass references or pointers. The second thing is, for that same reason, you don't want to have global variables, because you have a client machine and a server machine. A global variable in a client machine is meaningless to the server. Okay, so you cannot go and have global variables that are in two machines, because you cannot use the one that's on the other machine. Okay? So you should not use that either. Okay, you can use them for local procedures. That's not a problem. But in a remote procedure implementation, you shouldn't invoke global procedures that may be in some other process address space and so on. Okay? So these are some restrictions that are going to come because our code is now split between machines. Okay? They're in different address spaces. Okay? All right. So that's one problem. Okay? The other problem that we have to think about is essentially, what does the client stub and the server stub assume about the two machines? Okay? Now notice that I have said nothing about the client and the server. Should they be the same hardware? Should they run the same operating system? Should the client and the server be written in the same programming language? I didn't say anything like this, right? So what is allowed and what is not allowed? Okay? So RPCs don't make any assumption about the hardware platform. Okay? You can have the server running on an ARM machine or your Mac, which might be ARM, and you can have the client running on an Intel machine. Okay? This works fine. You can have the server run Linux, and the client can run Mac or Windows. You can deal with that too. Okay? So there are all kinds of hardware and software differences that RPCs can deal with, and that's a good thing, because you can't say I'm writing this service. Okay, if you say this is a web server and only Windows machines can invoke this web server because I cannot understand anything else, that's going to limit your application use. Okay? So you want some degree of hardware independence, OS platform independence, and so on. Okay? But that creates all kinds of complications for the RPC system, because you can ask, what if the client is 32-bit machine and the server is 64-bit machine? Right? I pass an integer. How is that going to work? Because integer mean two different things on two different machines. Okay? That's not it. You might have one machine that uses a big Indian architecture, another machine that uses a little Indian architecture. Okay? Big Indian and little Indian says, do you read bits left to right or right to left? What's the most significant and what's the least significant bit? Okay? So if you send an integer from big Indian and you now interpret that same bits on the little Indian, all your bits are flipped. Okay? The value of your integer parameter is going to change. Okay? Because you assume that I can make this work across hardware, but you have to deal with all these problems. Okay? And then there are issues like, what if I send some complex data structure? Okay? I have two-dimensional arrays of. Okay? How do I make sure that the other end knows what are the number of rows, what are the number of columns, in what order? Do you send them in row order, column order? How do you unpack that and reconstruct that? Because you're passing everything by value, remember. You're just passing some big amount, a parameter with lots of bytes, and you have to reconstruct whatever it is that you pass. Yeah. So all of this essentially has to be dealt with between the client and the server. Okay? You're going to do this through a few different mechanisms. First one is called marshalling and demarshalling of arguments. Okay? That essentially gives you a predefined way the client and the server are agreed to pack parameters and send them over. Okay? The client and the server also have something called an external data representation, or XDR format, that they agree to communicate with for hardware independence. XDR format might say, okay, you can't just send int, you have to send whether it's int 32 or int 64, so you know what type of integer you send over the network. Okay? You have to predefine that whatever you send over the network has to be little Indian. If you're big Indian, then flip the bits before sending it, so then you know whatever is coming is essentially XDR format, so you can translate it back. Okay? So you have to define these things a priori for you to get all of these good features. Okay? Otherwise, lots of things are going to go wrong if you just send some parameters and you just interpret them without knowing what the client machine was and what type of architecture it was, and so on and so forth. Okay? So once you define this format, you define marshalling of arguments, which says this is how you are going to send complex data structures and so on, then you get all of these nice features. Okay? You have a question there? Yeah. What advantage do you get over HTTP? HTTP is an application level protocol, okay, designed for sending requests and getting replies. This is essentially allows you to write any two applications that communicate with each other. The client side always HTTP. This is not HTTP. This is essentially using TCP/IP to communicate. You are calling methods. You are going to write a program, you may call a function, and then that function is going to be answered at the other end. I'm sorry? Yes, you are using TCP/IP, not HTTP. HTTP is an application protocol. Okay? So we are over time. I actually didn't realize that the clock is broken there. So we'll stop here for today. We'll continue next time. Okay?